All right, so video is being recorded now. Good afternoon, everyone. Can someone please confirm if you can hear me?
Yes, sir.
Perfect. I got a confirmation. Thank you very much. So this is lecture number 16 on stress maxima and minima. All right, so we'll start with a quick recap from last time. Then we'll spend some time on solving a couple of problems we had left from lecture number 15. That's last lecture. I gave you a couple of problems, homework problems. We will try to solve them in this class. Then we'll be spending a lot of time on stress maxima and minima. As I discussed last time, we have two different techniques to handle this. One is called the Lagrange multiplier method. The other one is through the use of Morse circles, which is the analysis technique. And towards the end, if we get some time, we'll work on splitting the stress tensor into spherical and divitoric parts. A couple of announcements before we start. So I uploaded problem set 2 solutions on Moodle. I'm sure you saw that. Also, problem set 3 has been uploaded on Moodle. So in case you want to try that, you can go ahead. I will upload the solutions to number 3 in a week from now. So let's give you some time to try that yourself. Then the reading assignment has also been uploaded. So in case you want to go through what's been done in this class, you can refer to the sections given in the reading assignment. These are the sections from the textbook, Mace and Mace, 2nd edition. In addition, I'll be uploading Moodle quizzes. That is one quiz per week to get a feedback on your engagement. That is just to say that you are able to access Moodle, you're trying to solve problems and so on and so forth. So this Moodle quiz is for engagement purposes only. It will not be graded in the final grade for this course. Then we'll have bandwidth feedback on Moodle. So I just want to make sure that you have enough bandwidth, internet bandwidth available to be able to access this course contents. Okay, that's just some formality that will be done through Moodle. Any concerns, any questions before we start? Okay, so let's start with today's lecture. So let's quickly go to the last lecture's slides and do a quick recap. So in the last lecture, we started with stress tensor. So we had a look at the local equilibrium equations and the symmetry of stress tensor and where it comes from. Then we solved a problem, which was just to understand how to apply the local equilibrium equations. And you also have a couple of problems regarding this available in problem set 3. Then we applied the idea of stress transformation. The general tensor transformation law was applied to second order tensors, which is the symmetric stress tensor in this case. Okay, and then I gave you a problem to show that sigma prime will be symmetric if sigma is symmetric. That is to say that if your stress tensor is symmetric, then the transformed stress tensor will also be symmetric. Okay, then we talked about the principal stresses and their directions. We talked about the normal and the shear stresses. We did a problem to find the principal stresses and principal directions. Okay, then I gave you a couple of problems. Another one, which was to show that the principal values of sigma, that is the 3 principal values that you get for a real symmetric sigma, are invariants. That is, they do not change upon the change in coordinate direction. And towards the end, we introduced maximum and minimum stress values. So this is where we'll start from today. So I'll come back to this one later. Let's solve the problems from the last time and then we'll start from here again. Okay, so the number 0 problem from last time was to show that if sigma, the stress tensor, is symmetric, then if we transform it, if we do an orthogonal transformation and try to look at it from a different direction, from a different orientation, then in the primed axis, we also get a symmetric stress tensor. So here's the solution to that. So for that, what we do is we write the tensor transformation law, which is this one, which simply lets us write the sigma prime values in terms of sigma values. Okay, then the problem is to be able to show that sigma prime ij is equal to sigma prime ji if it's given that sigma pq is equal to sigma qp. So it's given that the sigma, the non-primed stress is symmetric. You have to show that the transformed form of it, which is sigma prime, is also symmetric. Okay. It's quite straightforward. So you start with the form that's given in 1. So you start with this form and you apply the symmetry of sigma. So what we have done is we have taken this sigma pq and we have replaced that with sigma qp. That's the only change we've done. In the next step, we simply change the order of the terms. So I just, because these are scalars, so I can change the order. So I can write them in the opposite form, in a different order. So I write AIQ first and AJP later. Sorry, no, that's not what I do. I apologize. So what I've done is in the second step, I simply have so I've replaced P with Q and Q with P, because you can see that P and Q both are dummy variables. So they appear exactly twice, both of them. So I can write any other variable. So what I've done is I've changed P with Q and Q with P. So you can see that this AIP becomes AIQ and AJQ, the second term in the first equation, becomes AJP. And then sigma QP becomes sigma PQ. Okay, so we just change the order of P and Q in this case. Sorry, we just replace P with Q and Q with P. That's completely allowed because P and Q are dummy variables. Okay, then I keep the sigma PQ intact, and then I just move around the terms. So in this step, I move AJP first and AIQ second. So AJP becomes the first term and AIQ becomes the second term. So now if you see this form, so what you can see is that I can apply the tensor transformation law again here, except that in the on the right hand side, instead of having, I and J are reversed. So instead of having AIP AJQ, we have AJP AIQ. So that simply is nothing but sigma prime Ji. So that completes the proof that sigma prime Ij is equal to sigma prime Ji. All right. So if there are no questions, then we'll move forward. The next problem from last time was to show that eigenvalues of real symmetric matrix are real. Okay, I gave you a lot of hints, so we'll just proceed as per the hints. So to show that eigenvalues of real symmetric matrix are real, we first have to form the characteristic equation, because the eigenvalues are the solutions to the characteristic equation, which is which is given here. Okay. So we will see that we can see that this is a cubic equation. So we will definitely know that at least one of the roots is real, and we take that root as lambda1. So that's the eigenvalue which is real, and the corresponding eigen direction we call n superscript 1. Okay. So now what we do is, the trick here is that we find a new Cartesian axis, which is px1 prime, x2 prime, x3 prime, such that x1 prime, the x1 prime, that's the rotated x1 direction, is in the direction of the eigenvalue 1. Because remember that we can always, the rotation is arbitrary, so we can choose our own new axis. So if I take the initial axis as p x1, x2, x3, then I can form a rotated axis in such a way so that the x1 prime direction is in the same direction of n1. And then you can, if you want, you could choose any two, x2 and x3, as long as they form a right-handed coordinate system. Okay, so we know one thing for sure, that x1 prime is the same direction as the first eigen vector. So if it's the same as the first eigenvector direction, then so if x1 prime is in the direction of n1, then that means that the component of the stress vector in this plane is completely in the normal direction, because that's the definition of the eigen direction, the principal direction, that there are these special directions in which the stress vector is only in the normal direction. It has no component in the shear direction. So that means here sigma prime 1 2 and sigma prime 1 3 are both zeros, because sigma prime 1 1 is the normal direction component of the stress vector in the n1 direction, or the x1 prime direction. All right. So just as a reminder, if you remember that the stress vector in the n1 hat direction has the three components. Okay, that's how we define the stress tensor, the Cauchy stress principle, the Cauchy stress formula. So we define the stress tensor in such a way that the three rows are nothing but the three stress vectors in three mutually perpendicular Cartesian directions. So x1 prime is a new Cartesian direction that we have here. So sigma 1 prime, so sigma prime 1 2 and sigma prime 1 3 are both zeros, because they are shear stresses which are zero in principal plane. Okay, so I can write my sigma prime in this red coordinate system as this. Okay, so we can see that in the one direction we only have a normal, and since sigma prime is symmetric, that we have just seen, so the both column and rows terms other than lambda 1 are all zeros. Okay, and then sigma prime 2 2, sigma prime 2 3, sigma prime 3 2 and sigma prime 3 3 are as expected. Okay. So now we can write the characteristic equation in the sigma prime direction as well. So if I try to write the characteristic equation, that is nothing but sigma prime minus lambda I determinant is equal to 0. Okay, so what we're trying to do is we're trying to find the eigen vectors and the eigen directions of sigma prime. Okay, and we already discussed in the last class that the eigenvectors, and we'll show that soon, as which was a problem homework number 3, that sigma prime and sigma have the same eigen values or principal values. Okay. So if I write this, then I can write this in the characteristic equation form as lambda 1 minus lambda, and then and then the quadratic equation here. So what we've done is we have very smartly, we have separated the one of the roots. So we have factored the cubic into a linear and a quadratic. Okay, that's what our aim is here. So if we see the quadratic equation here, now the first one simply tells us that lambda 1 is one of the roots, which we already know. So the remaining quadratic equation shows that if we can find the determinant of this equation, discriminant of this equation, and we can very easily show that the discriminant of the quadratic equation is greater than 0. Okay, so if we show that, then what we have shown is that the other two principal values or eigenvalues of this equation are also positive, real. So positive discriminant means that the roots are real. So that completes the proof that all three eigenvalues or principal values are real for a real symmetric sigma. Any questions? Okay. Now, problem number 3 was, I asked you if the principal values of sigma are invariants. That is, if I try to find the principal value of sigma, and I try to find the principal value of sigma prime, which is nothing but the components of sigma in a rotated coordinate system, they should both give the same eigenvalues. Okay, the answer is yes. It's quite intuitive, because one way to think about it is that if you rotate your coordinate system, then there's only one direction or one coordinate system available where you have your principal coordinate system, and the corresponding sigma becomes nothing but a diagonal matrix with lambda 1, lambda 2, and lambda 3 as the 3 diagonal values. Okay, so that's just one special rotation of sigma. So you keep rotating your sigma until you find that principal plane. Okay, so that plane is distinct. Now the other reason, which is more mathematical, more analytical, is that you can write the characteristic equation, and what you see from this equation is that all the coefficients here, that is your the first invariant, second invariant, and third invariant are all invariants. That is, they do not depend on the direction. So if all the coefficients of a cubic equation are invariant, then the solution also has to be, or the roots also have to be invariant. Okay, so they will not depend on any particular direction. All right. So now we will move to the next section, next topic, which is on the maximum and minimum stress values. So let's quickly go back to the last lecture and the last 2 slides. So the problem we discussed was that if we have a point P and we define the normal and the shear components of our stress T, or the stress vector T, then sigma n comma sigma s, which is a combination. I mean, if I have the normal and the shear direction available, I can always find the T out of it. Okay, so given sigma n comma sigma s combination, I would want to find the direction n hat for which sigma n and sigma s become maximum or minimum. Okay, so I would want to find the maximum normal stress corresponding to any given direction normal n, and maximum shear stress values corresponding to any given direction normal n. I want to keep rotating my normal direction in all the directions until I find that normal or those normals where sigma n and sigma s become maximum and minimum. Okay, these are special directions where you have a very large normal or shear stress available, which can actually decide how you design your material. Because you would want the material to be strong. I mean, you can always design materials which are isotropic, that is, they are strong in all directions, or depending on the loading on the body, you can always design the material in such a way so that you can optimize the strength of the material in a given direction. So if the material requires to be strong in one direction, you only make it strong in that direction. Okay, so these are called functionally graded materials, which can be stronger in certain directions and comparatively weaker in other directions, which helps you save on the cost as well as the weight. So the state of stress at point P can be written as a combination of your normal directions and corresponding T directions, or instead of T, I can always write sigma n comma sigma s. Okay, that's what I wrote here. So state of stress is the is a list of all n hats and the corresponding sigma n comma sigma s points. So the first method, the method of Lagrange multiplier, we'll see how we can use that to find maximum and minimum sigma n and sigma s values and correspondingly the n hat directions. Okay, next will be the analysis method, which is where we try to do things using by writing equations, and these equations will then transform to our Mohr circles, which are nothing but which give us a feasible stress region. That is, if I keep rotating my n hat and I find all the points sigma n comma sigma s, they will form a bounded space in the stress plane. So stress plane is defined as a plane which has sigma s, so the shear stress in the y direction, and sigma n, the normal stress in the x direction. So for any given normal direction n hat, I will get one point in this feasible stress region, because you know that the state of stress tells you that if you have an n hat, then you have a correspondingly sigma n comma sigma s or a corresponding stress vector. Okay, so every n hat will give you one point in the stress regions. If you keep plotting all the points, then the locus of this point will give you a region, which is nothing but this shaded region that I've drawn. So we will see how we can actually derive this shaded region using analysis method. So the first method is the Lagrange multiplier method. So before we start using it, let us see what this method actually does. So in the method of Lagrange multiplier, so it's a method to maximize a function. So in this case, the problem is to maximize fx comma y subject to a constraint, which is an equality constraint in this case. The constraint is gx comma y is 0. Okay, so you want to maximize a function f, which is a function of two variables, or it could be n number of variables. For this illustration, for this discussion, we use two variables. So you want to maximize f, which is a function of x comma y, subject to the constraint gx comma y equals 0. So what the method says is that the solution to A, which is the maximum of f, or the point x0 comma y0, which corresponds to the maximum value of f. So the solution to A is also a critical point or a stationary point of the auxiliary function, which is given as this. So let's look at an auxiliary function L. So L is called the L is called the auxiliary function, which is nothing but fx comma y minus some variable lambda times gx comma y. So what you do is you take your function f, you take your constraint gx comma y, and you simply subtract them by multiplying g with some variable lambda. Okay, so L, the auxiliary function, now becomes a function of three variables, x, y, and lambda. So remember, lambda is a variable in this case. So what we are saying here in this method is that if I can find the critical point of this auxiliary function, okay, which is to say that so the critical or the stationary point for L is the point where all the partial derivatives of L with respect to x, y, and lambda are all zeros. That is del L by del x and del L by del y and del L by del lambda, they're all zeros. So that's called the stationary point or the critical point of this auxiliary function L. So if I can, what the method says is that if x naught comma y naught is a solution to A, that is our optimization problem, then there exists lambda naught such that x naught comma y naught comma lambda naught is a stationary point of L. Okay. So all we have to do is we have to find the L function by taking the difference of the function f and lambda times g, and we have to take the partial derivatives of L with respect to x, y, and lambda and make them all zeros. And that will give you conditions to find the value of x naught comma y naught, which is nothing but which corresponds to the maximum value of f. Is that clear? Okay, so let's move on. So let's apply this method of Lagrange multiplier to our problem, which is to, let's say in this case, maximize sigma n. Because that's what we're trying to do. We're trying to maximize our normal stress sigma n. Okay, so I can write sigma n as t dot n, because if you see from this figure, then this is your t direction, and sigma n is nothing but the component of t in the normal direction. So that is this component in the normal direction. Okay, so component of a vector in a given direction is nothing but the dot product of the vector with the normal direction or the normal unit vector. Okay, so that's what gives us sigma n being ti ni. And we know from Cauchy stress formula that ti is nothing but sigma ij nj. Okay, so I can write my t or the stress vector in any direction or in any normal as the dot product of sigma and n. So I can write my sigma n as sigma ij, nj, and I. Okay, so we have to maximize this sigma subject to the constraint that the normal is a unit vector. Okay, so remember that in this case, your variable, instead of having x, y, and z, your variables are n1, n2, and n3, because you're trying to find that direction at P where your sigma n is maximum. So you're trying to find a normal direction. So that is equivalent to saying that you're trying to find n1, n2, and n3, which are the three components of the normal direction, for which you get a maximum sigma n. Okay, so variables in this case are n1, n2, and n3, or ni, which is nothing but three variables. So the problem statement is you have to maximize sigma ij, ni, nj subject to the constraint ni minus 1 equal to 0. So we always must write the equality constraint in terms of inequality equal to 0. Okay. So what we see is that our g is ni minus 1. So g is a function of n1, n2, and n3, or g is a function of ni. Okay. Similarly, our f is the function that we have to maximize. So in this case, f is a function of n1, n2, and n3, or f is a function of ni, which is sigma ij, ni, nj. So we can write the auxiliary function as this function. sorry, it's not 0. So auxiliary function is f minus lambda g. So sigma ij nij minus lambda times ni minus 1. So the first thing you have to do is you have to form an auxiliary function. Okay, next what you have to do is you have to take del L by del n1 equal to 0. So to be able to write those three partial derivatives, we can write in a general form as del L by del nk, where k can be 1, 2 or 3. Okay, so now we simply have to take a derivative. So if I take a derivative here, just a second, I have to connect the charger to my laptop. All right. Okay, so the auxiliary function is given to us. So we simply have to take a derivative of that with respect to nk. So let me write the function here. So when you take the derivative of the first term with respect to nk, okay, so you apply the chain rule. So you get ni times del nj by del nk, and you get nj times del ni by del nk. Now sigma ij is not a function of n. Sigma ij is simply the stress tensor that's given to us. Now, in the second term, you have ni minus 1. So we already know that the derivative of a constant is 0. So we have the derivative of ni times ni, which is nothing but twice of ni times del ni minus del nk. Now we also know that del ni upon del nk is delta ik, because if I is equal to k, you get a 1. If I is not equal to k, then there are two different components of the n vector, and they are not dependent on each other because they are independent components of the vector n. So I can simply replace the term del nj by del nk by delta jk. Similarly, del ni by del nk becomes delta ik, and del ni by del nk becomes delta ik. Then you can apply this. You can expand this. You can expand this. You can apply the distribution property of multiplication, and then you get the term sigma ik ni by applying the substitution property of delta. You get sigma kj nj, and you get minus 2 lambda nk. All right. Now what we do is we apply the symmetric or the symmetry property of sigma. So if I apply that, then I can write sigma ik as sigma ki. That's pretty much it. Nothing has been changed other than this. So next, what we see is that sigma ki and I and sigma kj and j are both equal, because I and j are dummy variables. So if I replace the j term with the I term, then I get sigma ki and I twice. So I get twice of sigma ki and I, and the second term is the same. It's twice lambda nk with a negative sign. Okay, so that's the general derivative of L with respect to n. Now, if you remember, what we said was that if we make this derivative equal to 0, the partial derivative of L with respect to n is 0. So the solution that we get is nothing but the solution of the original optimization problem, or it gives us the point or the n vector for which my sigma n is maximum. Okay, so if I make this this whole thing equal to 0, then this is what we get. So I can write lambda times nk as lambda times delta ik ni, and if I take ni common, I get sigma ki minus lambda ki times ni equal to 0. Now this may seem a bit familiar to you. It's exactly the same as the eigenvalue problem. Okay, you have sigma minus lambda identity times the n vector is equal to 0. It's exactly the same. So what we see here is that the solution to this problem is the same as the solution to the eigenvalue problem. So remember, we're trying to find the n1, n2, and n3 values, or the n direction for which sigma n is maximum in this case. So since the solution to this is the eigen directions or principal directions, what we can say is that the sigma n corresponding to the principal directions or eigen directions are optimum. So that means we have found n1, n2, and n3 values for which the sigma n values are optimum. But we already know that in the principal planes, there's no shear stress. Okay, so the complete stress value or the principal values are nothing but the sigma n values. So we already know that principal values, we already know that principal values are the sigma n values in principal planes. So if we write three eigenvalues in the order lambda 1, lambda 2, and lambda 3, then our lambda 1 is the maximum and lambda 3 is the minimum value of sigma n. Okay, so what we have shown here is that the maximum value of sigma n corresponds to the maximum principal value or the maximum eigenvalue, and minimum value of sigma n corresponds to the minimum eigenvalue. And the corresponding directions are nothing but the directions corresponding to lambda max and lambda min. So we can say that if the directions are n1, n2, and n3, then the corresponding direction is n1. The corresponding direction here is n3. That's it, job done. So at the point P, we have found those two directions for which we get maximum shear stress and maximum normal stress and minimum normal stress. You take any other direction of n, the sigma n values that you will get will be between these two values. So I hope that this is clear. Now the next method we have in this case is called the analysis method. So what we do is in this method, we try to write the equations and graphically interpret them using Moore's circles. So let's proceed with that. So what we do here is that I mean this blue principal the blue coordinate axis that we have is the axis in which our sigma is defined. But we can always find the red coordinate axis, which is x1 star, x2 star, x3 star, which correspond to the eigen directions of sigma at the point P. Okay, so if I write my sigma in the principal coordinate system, then you already know that the sigma in the principal coordinate system is a diagonal matrix where the diagonal terms are sigma 1, sigma 2, and sigma 3, where sigma 1, sigma 2, and sigma 3 are the three principal values of sigma, and the rest terms are all zeros. So in this case, we have reordered the terms in such a way so that sigma 1 is the largest eigenvalue and sigma 3 is the smallest eigenvalue. So what we'll do now is we'll work in the red coordinate system because it's our choice. I mean, we can always work in the coordinate system of our choice as long as we can write or we can transform all the vectors in that coordinate system. Okay. So remember that what we're trying to do here is we're trying to maximize our sigma n or find the optimum values of sigma n. So this is the second approach that we're trying. So sigma n can be written as sigma ij, nj, ni, or in the symbolic notation or the matrix notation, we can write that as this. So if I take the product of the sigma tensor or the sigma matrix and the first vector and take a transpose of that, then I get this vector. So sigma 1 n1 as the first component, sigma 2 n2 as the second component, and sigma 3 n3 as the third component. And you have n1, n2, and n3 as the second vector. So again, if you do the multiplication, you get the sigma n scalar as sigma 1 n1 squared sigma plus sigma 2 n2 squared plus sigma 3 n3 squared. So that we'll call as 1. Now we also know that sigma s, so if you see the figure, then sigma is the shear component squared plus the normal component squared is the square of the vector t. Okay. So we can write sigma n squared plus sigma s squared as t dot t, which is nothing but sigma 1 squared n1 squared plus sigma 2 squared n2 squared plus sigma 3 squared n3 squared. Squared. Okay, and the third condition that we have is that since n is a normal, unit normal, so we have ni equals 1. Okay, so we see that we have three equations here and we have three unknowns, n1, n2, and n3, which is what we have to find. I mean, if you have a close look at the equation, then sigma 1, sigma 2, and sigma 3 are all given to us. They are known. They depend on the sigma value that you have been given for the point P. Okay, so what we can do is we can rearrange our 1, 2, and 3 equations, which is the equations that we had written for sigma n, sigma s, and n. If I rearrange them, I can actually write my n1 squared, n2 squared, and n3 squared in terms of the other variables. So going back, it's quite easy because you have n1 squared, n2 squared, n3 squared here. You have n1 squared, n2 squared, n3 squared, and you have n1 squared, n2 squared, and n3 squared here. So it's linear equations in the squares of n. So all you have to do is you have to solve the system of three equations, and you can get n1 squared, n2 squared, and n3 squared in terms of sigma n, sigma s, sigma 1, sigma 2, and sigma 3. Okay, so I'll tell you what we're trying to head towards. So what we want to do is we want to find the sigma n comma sigma s points, which are the points on the stress plane as a function of the various ni values. So the same thing that we have to find, for all the corresponding ni values, I would want to plot the sigma n comma sigma s values and find the locus of those points, which we will see that turns out to be a bounded region, which is bounded by 3 circles, call them Mohr circles. Okay, so we will do a graphical interpretation of this equation. Now, if I see the first equation, which is this one, if you look at the denominator here, so denominator sigma 1 minus sigma 2, and denominator the other term sigma 1 minus sigma 3, they're both positive because we have chosen sigma 1, sigma 2, and sigma 3 in the descending order. That is, sigma 1 is the greatest eigenvalue and sigma 3 is the smallest eigenvalue. So denominator of this equation number A is positive. So if we take that, then what we get is that since n1 squared is a positive quantity because it's a squared of something, so that means, and the denominator is positive, so the numerator also has to be positive. So what we get is the numerator is greater than or equal to 0. All right. So it simply tells us that we can actually rearrange and manipulate this equation into another form, which is the equation number A1, which is this form. Okay. Similarly, we can do the same thing for equation numbers B and C. Now let's look at what this equation is. So the equation is sigma n minus something squared plus sigma s squared is equal to something else squared. Okay, if you compare that with an equation of a circle, this is sigma n minus, let's call this sigma naught squared plus sigma s squared is greater than or equal to some r squared. So what this is saying is that this represents the region outside a circle. Okay, the circle has a radius of sigma 2 minus sigma 3 divided by 2, and the circle has a center which is given as sigma n equals sigma 2 plus sigma 3 by 2 and sigma s equals 0. So let's try to plot this. Let me do that here. We have the sigma s in the y direction and sigma n in the x direction, and I plot sigma 1, sigma 2, and sigma 3 on the x-axis. The reason I plot them on the x-axis is because sigma 1, sigma 2, and sigma 3 correspond to the principal values, which is nothing but which is purely in the normal direction. There's no shear component for principal values. So sigma 2 plus sigma 3 by 2 is a point here, and sigma 2 minus sigma 3 by 2 is the half of the distance between the two. So what this gives us is nothing but a circle which is centered between 2 and 3 and has a radius which is equal to 2 minus 3 by 2. And the region we are talking about is all the region outside this circle. Okay, so the stress cannot take any value which has a point sigma n comma sigma s inside the circle. It always has to be outside the circle. Now, if I go back to my equation number B, which is for sigma 2 and sigma 3, what I will see is that my equation comes out to be, I'm sorry, the first equation was having 2 and 3. In this case, we'll have 3 and 1. Okay, but what we'll see is that this will be less than equal to. Okay, so you simply have to do it yourself and you'll get that. And then the third one will give us for, so we've got 1 and 3, we've got 2 and 3, so we've got 1 and 2 here. Right? So what we see is that the feasible region is outside the circle which is formed between 1 and 2. So I form another circle between 1 and 2, and the feasible region is outside this, and I can form a third circle which is between 1 and 3. And what we see from this equation number B is that the feasible region is inside this circle. So that means the feasible space is nothing but the space the shaded space that I've drawn here. All right. So this is what gives rise to the Mohr's circles, the 3 circles, and it's named after Christian Mohr, who was a German civil engineer, who gave us this interpretation of Mohr's circles. So what we actually see, I mean, we already had drawn these circles last time, so let's use that. So what we actually see here, so in this case, we wanted to find sigma n max and sigma n min. So what we see here is that sigma n max is sigma 1, because if you see the shaded region, then this sigma 1 is a maximum normal stress that you can have. Similarly, sigma n min is sigma 3, which is the minimum normal stress you can have. And then sigma s max is the maximum value the shaded region can take, which is nothing but the radius of the largest circle, or the black one, which is sigma 1 minus sigma 3 by 2. Now, shear stress minimum, I mean, we can go in the negative direction, but that doesn't mean much. It's simply a change in the direction of shear stress with the same magnitude. So the minimum shear stress we have is 0. So usually what we do is we just draw half of this. So we draw whatever's above the sigma is equal to 0 side plane. So we are only interested in the maximum value of shear stress. The minimum value of shear stress is 0, which is existing on the planes where you have only normal stress, or the principal planes. Okay. So that ends our discussion on maximum and minimum values of shear stress. Any questions?